Hi everyone, welcome to lecture 36. In this lecture we'll be talking about the heat pump cycle. The picture here is a little cartoon of a residential heat pump. You can see all the various parts indicated here. We'll show a schematic of the cycle in just a moment. If you'd like to learn more about how a heat pump cycle operates, I encourage you to take a look at that YouTube site that I've listed here on the screen. It shows in very simple terms how a heat pump operates, and also the fact that you can reverse the operation of a heat pump and have it run as a refrigeration cycle, which is basically just an air conditioner. So it'll show that by changing a couple of valves, you can use your heat pump to operate as an air conditioner. So definitely take a look at that when you have a chance. It's not too long and it's easy to understand. Getting into the material, with heat pump cycles, the components are exactly the same as what we had for a refrigeration cycle. We still have a compressor that we put work into. So there's some work coming in. That compressor takes the working fluid, it's typically a refrigerant, takes it from a low pressure, low temperature state here at state 1, which is located over here, and it's shown here as in a saturated vapor state, goes through the compressor where the temperature and pressure increase to state 2. So you can see on the TS diagram, state 2 would actually be right about in here. It's a superheated vapor. Path goes something like that. The pressure at state 2 is higher than the pressure at state 1. So pressure 1 is down there. And you can see the temperature at state 2, of course, is much higher than the temperature at state 1. So the compressor adds energy into the working fluid. I've shown here state 2s. This is in case your compressor has an isentropic efficiency less than 100%. Then your real state 2 is going to be somewhere over here. So I've just shown the 100% isentropic efficiency state here as well. And then as you go from 2 to 3, you go through a condenser. This is where the heat is removed from the working fluid into the hot reservoir. So this would be the hot reservoir up here, and it would have absolute temperature, TH. The condenser is where the heat is going into the hot reservoir. This is what we care about in a heat pump cycle. What we want to do is put energy into the hot reservoir. I call it Q dot removed here, but you can call it Q dot H. It's the heat going into the hot reservoir. I say removed because it's removed from the working fluid. But this is what we care about in a heat pump cycle, is we want to get energy into the hot reservoir. For example, the hot reservoir might be your home in a residential heat pump application. You're trying to get energy into your home. Now, the working fluid goes through the condenser and constant pressure, so that means that we're going along the isobar on our TS diagram. And then at state 3, we're in a saturated liquid state, and that's leading into the throttling valve. So in the throttling valve, it's constant enthalpy process. As we go through the throttling valve, we drop the pressure and we drop the temperature. So you can see that in our TS diagram. So here's leading into the throttling valve, coming out of the throttling valve. You can see the temperature T4, same as temperature T1, it's a low temperature. T3, of course, is at a higher temperature. And you can see that the entropy increases across the throttling valve because it's a rapid expansion, it's uncontrolled expansion through the throttling valve, so the entropy, it's inherently irreversible, so there's some entropy generation occurring there. And now we're at a lower temperature and a lower pressure leading into the evaporator. The evaporator is a constant pressure process, so you can see here that we're going along the same isobar as the one for state 1. You can see the temperature stays the same. So at state 4, we're in a saturated liquid vapor mixture. State 1 is a saturated vapor, so we'll stay, as we add energy, we stay at the same temperature. We're changing phase somewhat. We're going from state 4, we have a lot of liquid, and state 1, we have no liquid. So you're just increasing the amount of vapor you have as you go from 4 to 1. The evaporator is where we pull energy from the cold reservoir. So here's the cold reservoir, and it has an absolute temperature of TC. So this is where we're pulling energy in from the cold reservoir into the working fluid. Now, in order for us to pull that energy into the working fluid, we need to make sure that the temperature of the working fluid and the evaporator is less than the temperature of the cold reservoir, so that we can make sure we get the heat transfer in the right direction. So the temperature of the cold reservoir would be somewhere here, right? So it'd be something like that. The cold reservoir temperature would have to be higher than the working fluid temperature so that we get the heat transfer in the right direction. And then the similar thing for the condenser. In the condenser, we want to make sure that the temperature of the working fluid here is higher than the temperature of the hot reservoir, right? Because we want to make sure the heat transfer is going into the hot reservoir. So the temperature of the hot reservoir might be something like this, so that we can get the heat transfer in the correct direction. Again, the purpose of a heat pump cycle is to try to increase the amount of energy going into the hot reservoir. That would be like our house. The cold reservoir might be the surrounding environment, for example. That's where we're pulling energy from. Even though it may be cold outside, like in the winter, there's still energy contained in the surrounding air, in the ground, maybe in bodies of water. Even though they're cold, they still have energy to them. So the idea is we're taking some of that energy away from the surroundings and moving it into the hot reservoir. So the way we define the performance of a heat pump cycle, the coefficient of performance, this is a measure of efficiency, we define it as the rate at which we're putting heat into the hot reservoir divided by the rate at which we're putting energy into our cycle. So what we care about again is how much energy we're moving into the hot reservoir. We want to move as much of that energy as possible for as little power that we have to put in. So we want this to be as big a number as possible. Another way you can view this cycle, we've shown this before, is we can draw it like this. This is our system. The system, this dashed line, is the same as this dashed line. And here's the power that we're putting in. Here's our Q dot H going into our hot reservoir, temperature TH, and then here's our Q dot C, the energy that we're pulling in from the cold reservoir, absolute temperature TC. So it's equivalent pictures. So this is how we would normally calculate our coefficient of performance for the heat pump cycle. The maximum coefficient of performance that we could get out of our heat pump is given by the following. So let me write that down over here. COP heat pump max. The COP that we would get for a reversible Carnot cycle. And that's given by the absolute temperature of the hot reservoir divided by TH minus TC, where those are absolute temperatures. So this is the maximum performance we could possibly get between these two reservoirs. Okay, it's the best that you're ever going to do. Every real system in here will have a COP less than this maximum value. So this is the best we're going to get. Now, let me just remind you of where this TH over TH minus TC comes from. It comes from our definition, actually, of our absolute temperature scale. If you go back in the notes some time ago, we had defined the absolute temperature scale in the following way. What we did is we looked at a reversible cycle. So the reversible cycle looked like this picture over here. And we looked at the amount of heat going into the hot reservoir divided by the amount of heat going into the cold reservoir. By the way, these could also be Q dots. Q or just Q dot, doesn't matter. And we looked at the heat transfer given in that reversible cycle, and we defined our absolute temperature scale as having the same ratio. So this was actually a definition. So I'll put the 3-bar equal sign. That's a definition. So we defined our temperature scale based on this kind of reversible heat cycle. So what I want to do now is let me go back to my original COP expression, and now let me write it down specifically for a reversible cycle, so that I have Q dot H reversible over W dot N reversible. Well, if I use the first law for this system shown up here in the upper left, the W dot N will be the Q dot H minus Q dot C. You can sort of see that if you take these two added together, the Q dot C and the W dot N added together will be the Q dot H, right? So W dot N will be Q dot H minus Q dot C. So I can rewrite this down here. Q dot H reversible on the top. The denominator is Q dot H reversible minus Q dot C reversible. And again, this going from there to there is the first law. And then now let me just divide everything through by Q dot C reversible. So that's just dividing everything through by Q dot C. Well, now you see we've got this ratio of Q dot H over Q dot C reversible, but that we can substitute in our definition for our absolute temperature scale. So this will now be TH over TC over TH over TC minus 1. Now let me just multiply everything through by a TC, and we're left with TH over TH minus TC. So that was just a quick review to show you where this expression comes from for our maximum COP that we could possibly get. Okay, and again, these are absolute temperatures here. Now, in a typical heat pump application, the TH, which would be like our indoor house temperature, that's more or less a constant value. Like, for example, we might want to keep our house at 68 degrees Fahrenheit or 70 degrees Fahrenheit. So that is not going to vary a whole lot. The TC is where we're pulling our energy from. So that would be the outdoors, for example. And you can see that as TC increases, then what that means is TH minus TC, assuming a fixed TH, that's going to get smaller. TH, of course, is always greater than TC. And then that means that our COP is going to increase, right? So if we can pull energy from a higher temperature source, cold reservoir, then our coefficient of performance is going to increase. And this is typically the case. When you look at the different types of heat pumps that are available on the market today, they generally, in three classes, you have air-to-air heat pumps, you have water source heat pumps, and you also have geothermal. An air-to-air type of heat pump pulls energy from the outdoor air and puts it into the air in your house. So this uses outdoor air for getting your energy. The water source heat pump pulls energy from a body of water, large body of water. So your cold reservoir might be like a lake, a pond, maybe a well. If you dig down into the subsurface water, you could use a well. Possibly the ocean, so it's pulling energy from a water source. And then geothermal pulls energy from the ground. Those come in two different styles. If you have a lot of acreage, a lot of land area, you can put your evaporator coils, it's basically just long tubing, you just dig it underground and just go back and forth below the frost line in your yard, for example. You want it down deep enough so that you don't have to worry about freezing of the lines and such. That's why you put it below the frost line. But you can pull energy from there, or if you're limited in acreage, you can dig straight down vertically and then pull energy from a little bit deeper. Now, the water source and geothermal heat pumps tend to have a higher COP performance, and the reason for that is because the cold reservoirs in those cases, those temperatures are more consistent. They don't vary as much throughout the year, and they tend to be warmer, because if you think about geothermal, once you get below the ground several feet, then the ground temperature stays at about 50 degrees Fahrenheit, somewhere on that order, year round. So it's a very consistent, relatively high temperature cold reservoir. Similarly, for a water source like a lake or something like that, in the wintertime, it can get cold, maybe between 30 and 40 degrees Fahrenheit, but it's certainly not as cold as the surrounding air. And again, that water temperature doesn't fluctuate a lot from day to day. So these water source and geothermal cold reservoirs tend to have consistent higher temperatures than the air-to-air heat pump. So here the surrounding atmospheric air can be quite cold. For example, here in West Lafayette, the air temperature in the winter can get down to 0 degrees Fahrenheit, and it fluctuates a lot from day to day. And as we just showed a moment ago, as we get higher cold reservoir temperatures, we'll have an increased coefficient of performance. So that's why you see the water source and the geothermal source heat pumps having higher efficiencies, because they have a higher cold reservoir temperature, and it tends to stay consistently high in temperature. As far as how we analyze heat pump systems, it's much the same as what we've done in the past. You can draw control volumes around each of the components, apply the first law, so you can see how much heat, for example, is coming into the evaporator, how much heat's going out from the condenser, how much power is going into the compressor. You can also look at compressors with an isentropic efficiency stated. We've done these kinds of problems before, so there's nothing new in the analysis of the heat pump cycle. The TS diagram, You've seen this sort of thing before, nothing new there. Similarly, finding the coefficient of performance for a heat pump, there's nothing new there, as well as finding the maximum coefficient of performance. If you look at the picture of the cycle and the TS diagram for this heat pump cycle, it looks exactly the same as what we had for a refrigeration cycle. All the components are the same, and the TS diagram looks the same. And indeed, a heat pump can actually operate in reverse to be an air conditioner. So a refrigeration cycle and an air conditioning cycle, they're the same thing. The whole purpose of an air conditioner or a refrigerator is to cool down the cold reservoir and move that energy to the hot reservoir, which would be the surroundings. So a heat pump can be run, I don't want to say in reverse, but it can be run such that it acts as an air conditioner. And so heat pumps serve double duty. You can either use them in the winter to heat the interior of your house, or if you, by a series of changing valves, you can change where the condenser and evaporator are. So in the summertime, your heat pump can operate as an air conditioner where you're removing heat from the interior of your house and then sending it to the outdoors. And if you take a look at this video, they show you how you can change the piping through some changes in valves to turn your heat pump into an air conditioning unit. So they serve double duty. So I've been talking about a heat pump as a way to heat your house, but they also have heat pump water heaters that are available now. So a heat pump water heater does the same exact thing as a heat pump that we've been talking about, except your hot reservoir in that case would be your hot water tank in your house. So these heat pump water heaters have tanks to them, just like a more typical water heater. And the cold reservoir in that case would be pulling energy from the interior of your home. So during the summertime, when the interior of your home is warmer, these heat pump water heaters work very well. They help cool your house because they're pulling energy from the interior of your house, and they're taking that energy and putting it into hot water. So during the summertime, the heat pump hot water heaters work great. During the wintertime, often they have to rely on an electrical element to heat your water, which is the standard way that a hot water heater might work. Because in the wintertime, you don't want to pull heat from your house because it's already cold, so you'd prefer not to do that. So you just use electrical resistance heating. Now let me just make one comment about electrical resistance heating. Let me draw a little electrical resistance heater here. So here what we have is some electrical power coming into like a resistor. This is a resistor here. That electrical power and electrical resistance heating is converted directly into heat. So this, I'll call that Q.H. That's the heat going in to warm your house. You may be familiar with electrical resistance heating if you have what's called baseboard heating, or if you do spot heating with a small little electric powered radiator or an electric heater. For an electric heater, the heat that's generated is exactly equal to the power that you're putting into it. They're 100% efficient, right? So whatever power you put into that electric heater just goes straight into being heat. It's 100% efficient. Now that might sound great. It's really not as good as you might think. Even though they're 100% efficient, a heat pump can even be even better than 100% efficient. And you can see that directly here for the COP, the way it's defined. The COP values for heat pumps can be on the order of 3 or 4. So you can see that we can get much better than the 100% efficiency for an electrical resistance heater. So here Q.H is equal to the power in. Here if the COP is 3, then the Q.H is 3 times the power you're putting in. So it's even better than electrical resistance heating. Now you might ask yourself, well, how can that be? The reason is, in a heat pump cycle, what we're doing is we're moving energy around. We're stealing energy from the surroundings and moving the energy through the working fluid into the hot reservoir. We're not converting it directly like an electrical resistance heater. Instead, we're moving it from place to place. And the way we're moving it is through the working fluid. Now, we have to manipulate the working fluid to move the energy around. For example, you have to pump it through the cycle. So the compressor does some of that. It pumps it around. So it takes some energy to do that. In addition, you have to make sure the heat transfers in the right directions at the evaporator and condenser. So here you have to make sure that you have the working fluid really cold. Here you have to make sure it's really hot. So the compressor does some work to make that happen. So there is some energy that you have to put into it to keep the cycle operating, but we're not directly converting the power coming in into heat going into the hot reservoir. We're actually just using this power to manipulate the working fluid. So the heat pump is more efficient than an electrical resistance heater because we're moving energy around rather than doing a direct conversion. Okay, now let's talk a little bit about various measures of efficiency for heat pumps, as well as air conditioning units. For air conditioning units, let's start there. So for an air conditioning unit, and again, you can operate a heat pump as an air conditioning unit, as we talked about just a little bit ago. Of course, we can always talk about the performance of an air conditioning unit using a COP refrigeration. Remember that an air conditioner and a refrigeration cycle are the same thing. We're trying to cool down some interior space, like at the inside of a refrigerator or the inside of your house. So they can be given by the COP-R, which will be Q dot C all over W dot in. Let me just redraw the picture here. Here's our hot reservoir, temperature TH. Here's our cold reservoir, temperature TC. So for an air conditioning or refrigeration cycle, our goal is to cool down the cold reservoir. So it's the amount of energy we pull out of that cold reservoir divided by the power that you have to put into it. The COP-R here as a measure for refrigeration or air conditioning, typically the COP is used for engineering or scientific purposes. It's a dimensionless number, no units associated with it. So that's what is commonly used in more engineering or scientific arenas. But in practice for like residential purposes and such, instead, people use what's known as an energy efficiency ratio. And that's abbreviated EER, energy efficiency ratio. It's basically the same thing as a COP-R. It's defined as, it's just defined in the same way, Q dot C all over W dot in. Same exact thing, except the only real difference, well, there are a few differences, one of which is the units. So a COP-R, this is dimensionless. There are no units associated with it. For example, in the numerator, you might use kilowatts. In the denominator, you would use kilowatts. But for an EER, they use a weird set of units. So the rate of heat transfer is given in BTUs per hour. So this is in the United States, so they have that weird English unit. And then for the power, that's in watts. So it's a combination of English and metric units that are used. So the units of EER are given in terms of BTU per watt hours. Okay, so it's a weird mix of units. You can see that the definition is the same as the COP. Obviously, the larger the COP or the larger the EER, the better off you are in terms of thermal efficiency. The other difference with the EER is when the rate of heat transfer and the power, when those are measured to get that EER value, they're measured for certain conditions, and particularly it's assuming that the hot reservoir is at 95 degrees Fahrenheit and the cold reservoir, which would be like the inside of your house, is at 80 degrees Fahrenheit. So the hot reservoir would be like the outdoors. The cold reservoir would be the indoors. That's at 80 degrees Fahrenheit. And then they also assume a relative humidity of 50% indoors. That can affect the heat transfer to some degree. So when they measure the EER, when they actually do that measurement, they do it under very specific conditions. Okay, so that's called the EER. Another very similar measure, that's a newer type of measure, is the seasonal EER. So that's called the SEER rating. Now the seasonal EER, or the SEER value, is the QC over the energy in over a whole season. The EER would be evaluated at an instant in time, like over a 2-minute period, let's say, whereas a seasonal EER is measured over a whole season. So this might be, since we're dealing with air conditioning, this might be over the whole summer. So it's the total amount of heat transferred out of your house interior divided by the total amount of energy that you've put in, evaluated over the whole season. And again, the units are this kind of weird mix of units. So the QC would be BTUs, and the W would be watt hours. So that in the end, the SEER units look the same as the EER units. It'd be BTUs per watt hour. It's a weird mix of units. The larger the SEER value, The larger the SEER value, the more efficient your air conditioning unit is. Now, the reason they do this kind of measure, evaluated over a season, is because it gives you a better idea of what's happening to the surroundings. So you still assume the same indoor temperature of 80 degrees Fahrenheit, but the outdoor temperature would fluctuate over the season. So you may have days where it's only 85 degrees, some days that are 90, some that are 95, some that are 100. So it's evaluated over a whole season, a range of THs. So let me make a note of that. The TH value changes over the season. And there are standards for how they vary that depending on your geographical location. So it kind of gives you a better idea of how your air conditioner might perform over the whole season that it's operating. Just to kind of give you typical values, the minimum EER values that you would get according to federal guidelines, those values should be, the EER should be greater than about 17.1 to 21.1 BTU over watt hours. So those are minimum values. For SEER ratings, a high efficiency value, so this would be high efficiency for today's air conditioning units, might be on the order of 18 to about 27.5 BTUs per watt hour. So that kind of gives you a feel for what sort of range you might have for these various quantities. So that's for air conditioning. So it'd be like your heat pump operating in air conditioning mode. As far as the heat pump operating in heat pump mode, we can still, of course, use the COP heat pump measure. So that's going to be your Q dot H over your power in. The federal minimums for that is it's on the order of 3.1 to 4.1. So, again, much more efficient than direct conversion using electrical resistance heating. Now, just like for air conditioning, instead of using that COP value for everyday use, for the heat pump, they use what's known as a heating seasonal performance factor. So heating seasonal performance factor, or HSPF. And that's defined kind of like the SEER rating for the air conditioning. It's just defined as the total amount of heat that you've moved into your interior space divided by the total amount of energy that you've put into your heat pump evaluated over a whole season. So it's very similar to the SEER rating, except here we're dealing with QH, and the units are the same as what you had for the SEER rating. It's BTUs for the heat that you moved, and for the energy you've put in, it's in watt hours. So HSPF units would be BTUs per watt hour. When people talk about a SEER rating or an HSPF rating, they don't say BTUs per watt hour. They just give the number. And a most efficient HSPF, so like a high efficiency heat pump might have an HSPF rating on the order of maybe 8.5 to about 12.5, somewhere in that range for current heat pumps. The idea behind the HSPF is, being evaluated over season is the same sort of idea with the SEER rating, that with the HSPF, what you do is you vary the cold temperature over the season. Because for the heat pump, it's the hot reservoir, your indoor temperature, that's assumed constant. And then it's the outdoor or the cold reservoir where the temperature varies over the season. So they would do measurements over a wide range of temperatures to see what you would get as an integrated response for the efficiency of your heat pump. All right, these measures of efficiency that I've talked about here, the EER, SEER, and HSPF, those are just extra. You don't really need to know those for this course. It's just extra information for you and kind of more practical related matters. All right, I think that covers it for this lecture, so we'll end it there.